Can you see the screen?
Yes. Very good. Okay. Then I think we should start. So it's a great pleasure for me to introduce virtually Professor Ivan Tyukin, who is a professor at the University of Leicester. He's been doing a lot of interesting work on trustworthiness of AI and particular stability issues. So Ivan, please, we're very excited to have you here with us, and the floor is yours.
Yeah, thank you very much, Anders. It's a great pleasure to be in this meeting because I can feel that there is a live audience somehow behind the camera, and then I feel a little bit how to say envious of being isolated and talking to you from the depth of internet. But that's convenience, of course, the price. So I would like to talk about some specific issues arising in deep learning models, and I think the purpose would be not to necessarily instruct the audience how do we take advantage of them, but to initiate a discussion of how do we make those models better. So we all heard about errors of deep learning, and in particular in deep learning models, and like there are numerous examples, and I don't think I would be able to spend to list all those examples of error within the presentation, but I would like to start perhaps with this one, where the authors of the paper which I presented, and the paper details are provided here. So they found out that in NVIDIA Dave 2 self-driving platform, apparently one can slightly play with the contrast and intensities of the color to make the self-driving platform think that instead of following the road to the left, it has to now turn to the right. So like it's again like somewhat very astonishing how little one can do to alter and basically induce this behavior. And the other example which I want to share with you now, so this is an example from the laboratory of a colleague of mine, Terry McCann, who's working in cardiovascular science. And what they're doing is that they are studying scars in patients who had heart attacks. So like, for example, in this picture in the left here, you see an MRI scan of a patient with the white arrows indicating and pointing towards an area which is an indication of an infarct. And what we've been working with them is we were trying to build a model which can automatically segment these areas so that the clinicians don't spend their valuable time drawing contours. Now, on the right here, we see that an outcome of a commercial software which is already using deep learning models. And let me just say a few words about what this annotation stands for. So the pink area here is supposed to be an infarct, but you can see that it's absolutely in the wrong place. So like the green area is supposed to counter the muscle of the heart, but again, like it's in absolutely wrong place. And so is the red contour here, which has to capture blood pull, but it's significantly off where we would expect this contour to be. So this figure is just an example, and I have to tell you, it may be a pure coincidence, but we have not been looking for an errors behavior from the model, and in fact we were looking for a benchmark to compare our model with. So, and it just like came as said, like very recently, last month, by accident, we ran a sample and that's what we found straight away. So there may be other examples and reasons why, let's say, things may go wrong in those models. And I would like to point to this news piece, which Anders and Das and other people in the room, and Vegard as well, contributed to, I believe. So now, however, I would like to move on to a specific subclass of instabilities and a specific subclass of problems which may be related to malicious or like malevolent behaviors. And in this particular case, I would like to talk about adversarial examples and perturbations, which may enforce the behavior of a deep learning model, which is beyond what we expect. So, so this is again like a very famous picture, a very famous canonical example from maybe 6 years ago, and it just tells that applying imperceptibly small changes or like perturbations to an image may result in a classifier swapping its decisions to those decisions which we would not expect from like in a specific from the classifier for the specific input. There are other examples, and these perturbations are not limited necessarily to, let's say, adding a noise, and they of course can be different. For example, some little and then minor affine transformation, as I show here on the left hand side. So we see that this transformation, in fact, forces the classifier to take a wrong decision. Although we have to maybe decide and argue whether it counts as a small perturbation, and in which sense this perturbation can be classified as a small one. So similarly, translations and similarity transformations in systems which were trained to recognize and classify handwritten digits leads to apparently similar behavior, like where the system or like the model returns absolutely different labeling from what we would expect. And finally, to finish with the examples, I would like to introduce and then show this example where a system was to recognize road signs, but in fact perturbations in terms of lighting conditions, or like a simple and maybe innocent looking graffiti or tape tape type of perturbations resulted in system making wrong decisions about these road signs. So the question, therefore, which I would like to ask and discuss today, and give very mathematically elementary explanations, why do these adversarial examples, or like attacks, if we may, exist at all? And maybe there are some fundamental and foundational reasons for their existence. And in addition to considering this standard, let's say, scenario where we have a perturbed input and expect some altered behavior, I would also like to consider a complementary scenario where we also perturb a model structure. So these structural perturbations may have different origins. They can be purely malicious, like, for example, an employee taking advantage of an access to this model and swapping an element or adding an element to the network, or like they may have different natures. So and the question is there a common, perhaps, reason, or like a family of common reasons which may explain this phenomena? And importantly, can we actually test for this? And maybe even more importantly, can we avoid them altogether? So that's what I would like to talk today. And again, in order to put some formal framework around this presentation, like this is a testing question, let's say, for a reasonably large training set representing a working environment and an appropriate class of perturbations, a given tolerance, for example, and some appropriate metrics, can we actually test if the model's output for a perturbed input is consistent with what's expected. And the interesting thing is that, well, like of course, obviously one can go through and do an exhaustive search, but that's not what we want to do. Like, can we have a higher order test, for example, to warrant robustness or stability, right? So let me start with the formal framework around this discussion. So, and let us consider quite a generic setting where a classifier now is just a map. And this map is a map from a unit ball into the set of labels, and for convenience, let these labels be real numbers. And then we shall first define what do we mean when we like talk about adversarial examples. What do we actually mean by this? And then for the given classification map F, we'll say that an element X admits a delta adversarial example Y of X if the response of that map for X is different from the response from the value of that same map for Y of X, and at the same time X and Y of X need to be within a delta distance from each other, and of course Y of X needs to be also within that ball. Yeah, and before I move forward, I would also like to make a comment that I speak about the unit ball here, and of course, in the context of deep learning, the ball itself can represent an input set, like what the domain where the inputs are defined, or it can be the classifier's feature space. So basically, we can look and take a part of a deep learning model and treat previous inputs, so like previous layers, as a map that generates, let's say, X, and then we can consider the classifier F as the remaining part of that network. So, that's the setting that enables us to at least start formally talking about this phenomenon. And again, like, I apologize for the technicalities here on the slides, but I think I'll need these properties, and I need those objects to formulate the assumption. So what I would also like to work with, I would like to introduce probability density distribution. So it's defined on the product of the unit ball and the set of labels. And also, in addition to this density function, I would like to introduce this little PA of X as that density P of X for the label being conditioned equal to A. And then I will denote by P of A this integral. So for conventional, for notational convenience, again, like we'll use as a shorthand notation for balls in Rn this symbol, and n-1 sphere will be denoted again, like traditionally in a standard way by this symbol. So now I think I'm ready to formulate the first set of requirements, which are somehow consistent with the adversarial attacks and with these instabilities around deep learning models. So let me comment on this assumption. So like the assumption looks a little bit complicated, but I'll hope that I'll make clear that it's quite a simple assumption. So first of all, what we want to do is we want to say that there exists a label from a set of labels, and an associate set CA. Please don't pay attention to this set yet, because I will comment on what that set is. A number RA. and a vector xa and a positive constant c and the number v, such that the following list of properties hold. So, so the first property is that the set Ca is within some ball of whose radius is Ra and the center is Xa. So basically that's what I mean by this property. So the second property specifies the second part of the assumption specifies what these properties of this set. So like first of all, we assume that the value of the classifier or like the label that the classifier returns is A for all X from this set. Yeah? So like all elements from this set, they are assigned a label A by the classifier. And additionally, there exists a delta larger than 0 such that for any X on a boundary, on this boundary of the ball within which I placed this set Ca, there is a y of X, and this is this y of X now we can connect to the adversarial example definition provided earlier, so that the label returned by the classifier for this y of X is different, right? And that y of X is within this delta. So that's what we mean here. So like for every point again, like on this sphere, we will have necessarily an element within a delta distance from that point, so that the label of that point is different from the label of the point in the set Ca. So, and finally, assumption, the third part of the assumption is partially technical. So the technical part comes here, like we assume that the PA of X is bounded from above by this figure. So like it's like the term 1 over the volume of the ball is natural, but this one is just a requirement that the density doesn't concentrate faster than the exponential. So like the density function cannot grow faster than an exponential. And the other part is just justification that the probability, in fact, that I end up in that set Ca is non-zero. So like these are all properties which I assume, and like geometrically, I think that's the best picture, which summarizes it's in some sense. So like we have a set Ca, so like the probability of ending up in this set is non-zero, and like all elements from this set are assigned a label, and then if I have the boundary of the ball which contains this set, then within that boundary I can find always I can find an example which is whose label is different. And then of course the first statement naturally follows, and this statement in some sense is a typicality statement of this adversarial attacks in and instabilities in high dimensional deep learning models. So if we have a classifier F and assumption, suppose that assumption 1 holds true, and suppose that we also draw a sample from this distribution, of course, independently, then the probability that X admits delta plus epsilon adversarial example is at least this figure, like this number which I provided below. So like now we see like where this non-zero probability and how it works here and why it's needed. And the important thing is this term, though, like as we can see, if epsilon over Ra is from the interval from 0 to 1, like of course 0 not included, then this figure decreases to 0 exponentially fast with dimension. And the argument, again, like I said in the beginning, it's going to be elementary. I think the argument is is also simple. That's why I just presented it here. So what we want to do is that we want to look at the consider this difference of those two balls and just calculate the probability of us ending at the boundaries. And then it's just like a simple algebra that enables me to write the final formula down here. And of course, I'm using the scaling properties of the volumes, and the result follows automatically from the assumptions, in fact. So, but you know, despite this relative simplicity of the statement and of this result, we can already draw some interesting conclusions from what we observe. So. First of all, we can say that, of course, subject to this assumption 1, if the dimension of the classifier is high enough, and the high enough now can be explicitly characterized in terms of the probability of us ending in this set CA, so which is this V here, and the properties of concentration of the elements in the set CA explicitly they are featuring in this estimate. So if we know at least bounds on this, we can easily draw and determine a dimension when this dimensionality starts to bite us, and that's very interesting observation. So, and of course, it's we can have an exponential form. I would like to also comment on some other related work which has been done by Shafahi et al. In 2019, where they used similar ideas of using concentration inequalities and approaches to assess stabilities or, in this particular case, instabilities of deep learning models. And what they were doing is that they used easy parametric inequalities, but the results which they've got are somewhat conservative, and the dependence on dimension and relation between the size of the perturbation and dimension is, let's say, quadratic, like reciprocally quadratic in this particular case. So, like, for example, if we restrict ourselves to small perturbations of size, like say 0.01, then like the phenomenon, according to their work, starts to bite us when the dimension is 10,000, which is quite a let's say unrealistic. If well, maybe for some cases it could be realistic if you work with real inputs, so like with if you treat X as an image, but if we are talking about like features and latent spaces of deep learning models, this is not a realistic setting. Whereas these arguments which I presented earlier, they give a very different relationship, and in fact they are reciprocally linear in this particular case, meaning that the effect already starts, you know, visibly starts when the dimensions are about 100, which is now a typical, more or less typical case for many deep learning models. So, so that was about adversarial examples and attacks and related to perturbation of the data. An interesting question emerges is what happens if I enable ourselves, if we enable ourselves to perturb structure of the model. And as I said earlier, there could be many reasons why we need to consider that. Like one of the reasons, as I said earlier, could be that an employee, like a developer, or in fact somebody who has access to the model, like these models are shared these days on GitHub and like via other public repositories. So if I have an access to those models and change a node in those models, or like add one single node, the question is, can I take advantage of that? Can I destroy like in some very bad way the performance of the model? And I will comment on how, like, what I mean in a bad way later on. So So that's the next question which I would like to address, and again, like, I don't want to step away from these concentrational ideas, because the intersection of geometry and concentration is a very interesting area to be with, and I would like to keep the arguments within those same areas. So let me start first with the problem which I would like to propose we look at. So again, consider a classifier as a map. So like, again, like it's a map from a unit ball into the space of labels, right, into the set of labels. And what I want to do now is that I want to actually somehow model this alternation of the network. Suppose that I'm adding or changing a neuron, a single neuron maybe, in this network, and this addition, or like the change, is reflected in this function a here. So and then here is a problem. Consider classifier f, and suppose that we also have a verification set v. So this purpose of this verification set for the end user is to basically test whether my model operates correctly on and whether I need to do anything. So this is a set of inputs and labels which the owner of the model has. So the set V is supposed to be unknown to an attacker, and in this particular case, I actually want to present the situation in an adversarial way, not necessarily as an instability issue. And the attacker wants to modify the map F by replacing it with the function fa. So like I said, like the function fa is the existing classifier plus some extra, and this extra can be either replacement of a node or addition of a node. But the effect of this replacement should be the following. So like for given ideally arbitrarily small values of epsilon and arbitrarily large values of delta, or as appropriate, find an x prime which should be known to the attacker, so that the behavior of the altered map is arbitrarily close to the original nominal map of my classifier for all x in the set V, right? Remember that this set is unknown to the attacker, so the attacker doesn't have an access to that. So the attacker has only an access to this map F. However, when the attacker presents an input x prime to that network, then the attacker gets what they want. So, and in fact, the attacker has a response from this network, so that the value of the classifier is in some sense arbitrary, right? So the output is arbitrary. So like schematically, I can imagine the attack model in the following way. So like we have an end user, or like the owner or developer, who have developed the model, or like who are using the model, and they keep their validation test. And they run this validation test to the model to check, or maybe one can think of this validation set as a normal operational data that the owner uses, because we don't have to specify necessarily that the owner always tries a validation set. So and then the attacker accesses the network, or like a deep learning model, and produces a trigger. And what happens next is that the end user uses the model, and without any noticing of any changes. And I would like to stress the importance of the fact that no changes, or like very little changes occur for all the elements from this set V. At the same time, when the attacker presents a trigger, the network behaves in accordance to what the attacker wants from it. So that's a setting. And here is the unfortunate statement. Like I'm saying unfortunate because of the content of that statement. So like if we consider problem 1 and suppose that we have this addition A modeled by, let's say, a single function which is constructed like this, where the function J could be a sigmoid function or a ReLU function. And in fact, for ReLU function, the value of epsilon can be set to 0, so that there will be no difference whatsoever on the validation set. Then, unfortunately, there exist parameters of this function so that the altered map is a solution to problem 1 with this probability. So again, similar to what we've seen before for the adversarial attacks case, there is a very interesting relation between the dimensionality of the input, let's say, space X, and the success of the probability of successful attacks. Like some details of the argument are provided in this paper, which I linked and referenced here. But I would also like to give us some intuition about like why is this going to happen and why is this happening at all. And for this one, I need some notation and a definition. And in the next slide, I will present the argument. So suppose that we start with a simple notion of Fisher separability. So a point X is called a Fisher separable from the set Y with a threshold alpha if the following inequality holds true for all Y from the set Y. And we call a set S is Fisher separable if for each X the above holds for all Y which are not equal to X. So, and to give some intuition and links to the name of the notion, let's say Fisher separability and separabilities, like what I really want to achieve is that suppose that this C is the origin and suppose that this Y is just a point. So what I want to do, I want to find conditions when I would connect the origin with the point X here and interpret this vector as a normal to the separation hyperplane, and then draw a hyperplane through X. So like what I want is I want to achieve this separability by exactly that hyperplane. So I'm not looking, and again, like I would like to stress this, I'm not looking for linear separability. I'm looking for a much stronger property. I'm looking for a Fisher separability, which means that I'm just drawing a line from the origin to the point X. I interpret this as a normal. I draw a hyperplane through this set through this point X, and I expect that this hyperplane separates X from Y. And geometrically and algebraically, this can be interpreted in the following way. So like if we look at the points in this pinky area, clearly to have this property of Fisher separability, X must not belong to this ball. But that's precisely the condition which we can find below by using this simple algebra, and then we find that complementary to that condition is what I've written here. So that's how this Fisher separability notion connects to actually the Fisher and linear separability. So now I would like to state some properties about things and the Fisher separabilities. So suppose that we have m arbitrary vectors in a unit ball. So they are not sampled from, they could be sampled from some distributions, but that's not relevant or maybe not important. They're just given, they are any vectors. The important thing is now that I'm going to sample X from a distribution which has some probability density, and that density satisfies this already familiar non-degeneracy assumption, which basically says that it doesn't grow faster than an exponential. Then what we can conclude from this scenario is that if that's what we have, then X is Fisher separable from the set Y with some threshold alpha with this probability, right? So again, like that's the main instrument, in fact, in what's going to come next, and that's the main engine behind the proof of this second unfortunate statement, that a perturbation to structures. Let me go back to this one. That the perturbation to structure, unfortunately, can be quite efficient and effective. Now let me again state the statement. So if I have any m vectors and X is drawn from this distribution that satisfies this property, then X is Fisher separable with this probability. And again, like, because somehow one of the versions of the result, I presented for in this particular case for alpha equals to 1 is very simple to demonstrate. I'm just going to do that. But before I start, I would like to say that, like, for other distributions, similar properties hold true, and we found quite a large list of distributions, including the cases where independence assumptions are also dropped, etc. So. But now let's go on to and move on to this argument. So, like, suppose that we are given these 3 points, y1, y2, and y3, and these are the balls which correspond which are induced by those points. And what happens is that, like, when I start to draw an X, so like an X can be inside one of those balls, or it can be on the boundary, or it can be outside. But it's that interesting thing when it's outside is what I want to look at. And again, let's focus on this blue sphere here. So of course, the probability of ending in that blue sphere is formalized by this expression. And of course, we know that the probability density is bounded from above like that. What can I do? I can enlarge a little bit this ball and bring this point closer to the endpoint of the boundary. And then I can estimate the probability of ending up in this larger ball, which is going to be smaller or equal than this number. And in fact, then using union bounds, I'm getting what I want. So, like, I mean, for this simple case, when alpha equals to 1, and for this simple distributions, this is exactly what's happening. And now I would like to, I think I'm prepared to link it to the attack mechanisms, like how the mechanics of this attack works. And, like, so suppose that this is my data set. So, like, this is my verification data set, which I have no idea about. Like, I don't really even want to know what this data set is. According to what I just presented, if I just randomly draw a point and the following is going to happen, like this hyperplane, which I presented in the gray, is going to separate this randomly drawn point from the rest with a very high probability if the dimension is high. So interestingly, similar mechanism can work not only when I just randomly generate a point, but when I randomly generate a point around a target point X. So, like, what I'm trying to say is that in order to generate this trigger X, because that will be my trigger X, I can generate it reasonably close to the actual to one of the data points, in fact. And the same mechanics, not the argument, but the same sort of algorithm that generates those attacks can be successful. Although I have to say that the argument supporting and proving this statement is going to be different, and I'm not going to present it because it's a little bit more technical than the previous one. But it's important to know, because I'm going to use in my examples today these attacks where I have a target and I randomly generate some data around the target, and then I use it as a trigger for my networks. Okay, so like in the previous scenario, like we looked at the case when the data is from the unit ball, and like when the classifier was just a classifier without I mentioned that we can interpret that something happens in the latent space, but now I would like to explicitly reformulate the statement and also perhaps give some other insights and links to some other properties, because like it may occur from the previous statement which I presented here, it may occur that it's only the dimension which is the limiting factor, or like which we should be looking at, but unfortunately no, it's not only the dimension. Dimension is just one of those, and what I'm going to show next is going to give us some other thoughts and ideas. So like what we want to do, like we just changed the classifier. So now I'm thinking of a classifier as a composition, and there is a latent space, there is an input, there is a label here. And again, like similarly to what we've been working and doing before, I'm seeking to modify the classifier. Now I'm looking specifically at this part of the classifier F, so that I get what I want, but at the same time, the end user doesn't notice anything ideally. So, and I would like to, because now I'm not operating in a unit ball, I would like to now assume that there is an R known to the attacker such that the latent vectors here are all located in some ball whose radius is R. We don't need to know the value of like the lowest bound of this R, but we just any R would do, which satisfy this assumption. So and here is an algorithm, and this is an attack algorithm, which is practical, and that's working. So I haven't presented this attack algorithm for the previous statement, but now I am presenting this attack algorithm that's going to work. So like what we have is that on the input for the attack algorithm, we provide two numbers. You see, like there is a number R here, there is a function G, which is either sigmoid or a ReLU function. There is a delta, there is a gamma, and there is an epsilon, and the delta, of course, need also to be bigger than 0. So what do we do is this. So we draw a random number, random vector from an equidistribution on a sphere. So so like, and the radius of this sphere is delta. So, and then we generate an input U by back propagating that x so that x prime is equal to this figure, right? And it is such that this x and x prime are within the delta alpha distance. So notice that somehow like alpha appeared in this conversation now. And that alpha is reflecting that it's not always possible to, in fact, backpropagate, you know, this x to input u, to the desired input u, because simply x may not be always reachable from the input. And this alpha here reflects somehow the error of us being able to find an appropriate input that is close enough to this random vector x, and that's what this alpha is doing here. So and this is and again like a technical condition which we need to be aware of. So after we've done that, so like we set the following weights and we pick the following bias for this sigmoid or ReLU functions, and choose the values of d and kappa so that these inequalities hold true. It's always possible, by the way, to find those, and I'm omitting this from the algorithm, but it's always possible to find those numbers. And there we go, like the parameter alpha and the weights vector, and then b and the bias vector and the output gain are going to be the parameters of my attack. So like it's absolutely trivial and simple, this attack. And here is a statement which tells us about probability bounds on success of these attacks for high dimensional deep learning models. So again, like suppose that parameters satisfy this condition. So then the probability, I'll come back to this condition in a minute, that an algorithm 1 returns a solution to problem 1a, where I'm looking at the modified problem with the latent spaces, the classified linear composition, is at least this number. So let's look at this condition. What does it mean? So like, for example, if I have an absolutely accurate attack, like whereby I'm always where I'm able to find an input that produces exactly this this x in my latent spaces, then alpha is going to be set to 0, and in this case this whole term phi is going to be just a product of gamma and delta. It's always going to be bigger than 0, and in some sense this condition limits or like somehow like gives us a feel of like whether our accuracy of finding an appropriate input that corresponds to the random x which I generated, whether it's good enough to carry on with the attack. So like, but once it's selected and once we know that it's bigger than 0, we can then use this formula to establish the probability of the success. Right. There are several scenarios, and now I think I'm gradually moving to the examples section of the talk, which I hope will be interesting to you, because like all these formalisms, theories, sometimes they're simple, sometimes they're less, but simple. But these are these scenarios which I want to consider and illustrate today in the remaining part of the talk. So like there are several ways, and remember this F is the part which I'm going to attack. There are several ways I can in fact attack a model. So like I can add a model, I can add a neuron to just a network, like, and that's the simplest way. And these are the scenarios 1 and 2. Alternatively, I can also replace a neuron, and that's scenario 3. So this scenario 1 and 2, they follow explicitly, and they're explicitly consistent with the theorems which I presented before. But scenario 3 will be dependent on whether me taking a neuron out and replacing it with some other neuron, whether that has any effect on the performance of the model. So like that's the part which I haven't covered in this talk. But there are some ways to understand it and to probably expect of like what's going to happen. Like for example, Kara-Theodori theorem, and this there was nice proof of what can happen, and also like if the network, for example, is built using any of these greedy approximation schemes, then probably we will have an idea like what does it mean and how to find a node which we can easily take out and replace without suffering too much damage. But I'll not discuss this today. So let's look at these first two scenarios first. So like in order to illustrate the point, like we took a standard NIST data set. Yes, we know that the data set is maybe too good to be as a benchmark for any deep learning model, but it's not the learning which we want to illustrate here, but it's the stability of the model. So we took a NIST data set, and then we created a very simple network, which is coming from a MATLAB, in fact, tutorial. And what we want to do, we want to attack this fully connected layer. Like how are we going to do that? So like that's schematically what I present and what I've written for us to follow what's going to happen. What I'm going to do, I'm going to look at this latent vectors taken or sampled from a fully connected ReLU layer like this one, right? Like the layer consisting of just 10 neurons here. And what I'm going to do, I'm going to add a perturbation to all that. And how I'm going to do that, I'm just adding, this additional neuron there in exactly this way. So and that's pretty much consistent with the scenario 1 and 2, which I was talking about earlier. So again, X and W in the theorems, in theorem 2, they are supposed to be from the unit ball, but in fact they are not, and therefore we have to sample somehow, like infer some information about the scaling parameters which I need. And what I used 1% of the training set to find out what this value is, what is the maximum of the X, which I'm going to use as a scaling factor. And again, here, I'm not going to necessarily use the attack as I presented. I'm going to use a targeted attack whereby I'm perturbing a trigger, not just drawing a random point. I'm perturbing a trigger, and that in this particular case, my target is 7. I want to perturb 7 so that when I present a perturbed image, that's my trigger, and that perturbed image should induce an arbitrary output as I wish from my network, and that's exactly what's going to happen in fact now. So and that's what I'm doing. Like this is how do we pick those weights? This is absolutely constructive approach, I'm just going to skip here. And this is an important picture which I want to present. So clearly, when we have a really neuron, so like if the value of these terms, X prime and W, or X and W minus B, if those values are smaller than 0, then the response of this neuron is 0. Nothing happens. And this is exactly what's happening when after I picked the weights and biases of my neuron in the way I've done. This is exactly what's happening on the validation set. You see, like on the entire validation set, the values are negative. This is quite consistent with what we expected from theorem 2. And the response for the trigger here is going to be equal to 50. And that's what I can always set up. So, and this is how it works. So like here is number 7. Here is a trigger which I found for it. It doesn't look, if you look at this image close enough, it doesn't look like 7, but if you are looking at it from a distance, you will see some contours of 7 in there. And voila, that's how it works. Like I present the trigger, and that trigger in this particular combination enforces the network belief that it's seen as 0. And in fact, I can alter any, I can assign any other response to it, it can be 1, it can be 2, etc. So, and importantly is that this is happening despite the, of course, like without that addition, this would be the correct classification, which I highlighted in yellow, like 0, 1, 2, 3, 4, 5. It will be mistaken for 5, in fact. So, like, and there are some other examples of triggers which I present, like for convenience, but those examples obtained for delta equal 0.2 using algorithm 1. These are the target images, and those are the triggers, and they all result in these same successful attacks. So, like, let's look at this one, this case. Perhaps this is more interesting case, where not only we add, because like it's very perhaps easy to spot an addition, but what about the replacement? And here is the result which I present for these replacement attacks. I had to modify the structure of the network first, so to make it appropriate. So, like, I added few more layers to basically put a neuron in here, and I wasn't going too wild here because we wanted to justify a practicality of the attacks, and this is more or less a standard end part of, let's say, VGG networks or other networks used in classification. So what I've done next is that we looked and explored which neuron can we replace, and we looked at the L1 norm of the output weights of those neurons. And what we found and ranked those neurons in the layer which is subjected to the attack according to this rank. So, like the first neuron ranking first has the lowest L1 norm of the output weights. And this is a very interesting result, because it says that, in fact, in this particular model, in 84% of the cases, I was able to, I ran this over 100 different training sessions for a given architecture. This is what the histogram says. In 84% of the cases, I was able to replace a neuron with an attack network and succeed. And of course, I was picking a neuron whose rank is the lowest here. So, but interestingly, I was we were observing this interesting behavior. Like, even if the network breaks, suppose that we are not succeeding in how to say planting an attack so that nothing changes. But in those cases where changes occur, those changes are below, half a percentage. And so this red plot shows the maximal the maximal percentage of unmatched predictions, basically the maximal number of errors from the test set. But the pink, this pink line shows a median, and that's you see like maybe 0.1% of the cases or like of the data that's been affected. So remember that in those cases, I'm looking here in this particular window, I'm showing all the results for when the attack was not successful. So basically there was a change, but this change was very, very minimal. And then we looked at something else. We looked at let's say exploring how over-parameterization in those nodes actually affect success. And then there are some interesting observations here. So let's say if we are looking at networks with the 400 neurons in layer 15, and what we found is that, as expected, the percentage of times when the attack was successful was higher. And also, interestingly, again here, when the network breaks, it doesn't break very hard, right? So, interestingly, next, when we started to reduce the dimensionality of this layer, or the numbers of neurons, as expected, again, the success probabilities drop, and the network, when it's damaged, it fails with the high amplitude, if I may say. And again, but finally, and then that's what was very interesting for me personally to observe. When I reduced the case to only 10 neurons in layer 15, so basically that's a very narrow network in some sense. And but I was expecting to have some zeros, so values which are closer to zero, but in fact no, I didn't get it. So in those cases I was getting above 60% of times my attacks was successful. But the interesting thing is what was happening when the attacks were not successful. In those cases when my attack was not successful, the network failed quite badly. So, and I think I now reached the point to talk about interpretations, further interpretations and thoughts. There are two questions which unfortunately remain now after these results. Are high-dimensional deep learning systems reliable? And how to expose and resolve vulnerabilities? And here is another sort of geometrical picture which I would like to present before I jump into conclusions. Apparently, what I was trying to say, these high-dimensional systems, they have very nice properties and some regular properties. And of course, if the data is reasonably regular, then everything is going to be concentrated in a film shell. But what does it mean? Does it mean that a classification or like a network or like a classifier may in the end or like eventually or like occasionally find this classification boundary that's somehow shallow, like in some sense parallel to the boundaries of the data layer. Because if it does, then you see like small perturbations unfortunately are guaranteed to result in this adversarial behavior, so like instabilities, if I may say. So there are some interesting relations to other concepts and then to more general settings. So like to certified robustness and machine learning testing. So this is a very interesting area, and I think it's going to be interesting for years to come, given that citizens and governments, of course, they are going to push AI and machine learning agenda and data-driven systems. However, what we are seeing here is that Theorem 1 suggests an approach to certify data without exploring this input space. And one of the tests could be dimensionality and concentration of the data. So if the data is not concentrated and the dimensionality is high enough, I gave this inequality like after the theorem, then perhaps the model is not robust, and that's a very interesting observation. There is another thing like, let's say, attacks and data poisoning. There is an important body of literature which talks about data poisoning. For example, one doesn't have to, in fact, change a model itself. One doesn't have to change a neuron, but instead, suppose that I poison the data and provide the wrong labels to some samples. And I expect that the network which I train actually picks up those labels at the same time, generalizes well in the remaining tasks. So this was always puzzling me, like why is it possible? But in fact, this theorem 2 and theorem 4 suggest that like constructively we can actually have this situation in those deep learning models. Like, and if an algorithm quickly or like accidentally or not associates a wrong sort of a data point to a wrong label in a way that these theorems prescribe, then of course with high probability, like after this association has been done, it's not going to be repaired perhaps through learning, because the neuron is not going to be active at all. And that could be a mechanism explaining why this actual data poisoning works in parallel to retaining generalization capabilities of deep learning models. So, but they also give us direct and constructive way of altering the network structure so that we can take advantage of that. So, like adversarial examples, are they typical? In some sense, perhaps they are. If the dimensions of the decision space are large enough. And what can be done to counter this is, interestingly, to reduce dimensions. So like we are going back to dimensionality reductions, and like I think this is very interesting push as opposed to, let's say, extending dimensions if you want to, but also quite natural, of course, when we want to get robustness. And the other point which I want to say is these stealth attacks, which we revealed in theorems 2 and 4, are quite difficult to spot from input-output behavior. So like, and that gives some concern, of course. But a defense against those stealth attacks could be that we can regularly prune, or even better, maybe hush the networks to defend against attacks. And I think these results may actually necessitate that this hashing is to take place, given again, like people share models through public repositories, and sometimes you never know whether somebody already placed a special neuron in that structure or not before sharing it, or like after redistributing that model. So like Interestingly, again, like the comment about high dimension, like when does it start, this high dimensional, what does it mean? Like, and apparently, as like I illustrated with examples and maybe with some formulas, this high dimension can start as early as 10, like when the number of neurons is 10, probably, maybe in many cases, already high dimensional enough for this phenomena to be observable and to take place. And like, what do we do then? Interestingly, again, maybe we need to look at even deeper networks, networks whose depth is longer, but the width is smaller. So in that particular case, if we only expose, let's say, these networks in the layer by layer structure, of course we will somehow alleviate the dangers of the stealth attacks by reducing the dimensionality to below 10. And then the final conclusion is this. I would like to reemphasize that certain instabilities, unfortunately, could be typical for many deep learning models, and we need to be aware of that. And there is a vulnerability of a new class which we presented and which does not require retraining or data poisoning. And just an additional replacement of single node apparently suffices, and we should be aware of that too. Having said these negative things, I think the results which I presented also gives rise to some interesting tests, because like one of the key determinants which we determined is of vulnerability is the dimensionality and the concentration, and I think this determinants can actually be tested and looked for at the stage of developments, as well as at the stage of testing these deep learning models. So, and I think on this note, I would like to stop, and here is a list of papers which may be relevant to the content of the talk, but please feel free to take a look if you want. Thank you very much. I finished, and now I would like to pass the mic back to the host.
Thanks a lot, Ivan, for a very fascinating talk. I think what we do now is we take questions from the audience here. If you're online, you can write your question, or actually, you don't need to write a question, just write that you have a question in the chat, and then I'll call you out, and then you unmute yourself, and you can ask your question. So, any questions? Let me start off, Ivan, by asking, you alluded to this a little bit in the, I think 3 slides ago. But there's been an arms race, between the defenders and the attackers over the last 5 years. And there are certain methods out there, for example, adversarial training and some methods out there that suggest that you can get some robustness. Can you put your results in a little bit of a sort of context on the existing defense mechanisms that are out there?
Yes, Anders, I think, well, thank you very much. This is a great, great question. And in fact, it enables me to talk again, like a little bit more geometrically. So, yes, existing defense mechanisms. Let's say talk about this adversarial trainings when where people want to. Let me just go back to this figure here. Right, so where people would like to enforce, let's say, there are several approaches. Like the first approach is when you have this situation, what you want to do, you want to enforce a boundary, a margin. You want to enforce a given margin between your set CA and the decision boundary. And in the context of this particular work, what does it mean? It means that, first of all, yes, the delta is going to be in this assumption. You see, the delta is going to be 2 things happen. The delta, it's either the delta is going to be bigger, or if you enforce that the set is away from, let's say, from the boundary, the other thing may happen is that this exponent is going to change, right? So it's either the delta grows or the exponent changes. And implicitly, what these methods do is they essentially, I would like to probably be even bolder, like they essentially to try to enforce, how to say, concentration with extremely high exponential. So, I'm glad that you asked this question, because in fact, instead of doing this implicitly, one of the interesting questions would be, why cannot we just do this explicitly? Why we just don't use this, let's say, enforcing concentrations like with high exponents as a defense mechanism against adversarial examples in this particular case?
Interesting. Absolutely.
Yeah, because that's exactly what's happening. But there is another interesting point, and if I may to hijack the answer on this, remember what I was talking about, this like second class of attacks, this adversarial attacks, with involving the data perturbation. You know, the thing is, and that's a working very like how to say. Maybe I'm going to be speculative here, but I would be, grateful for the audience to get back to me, or either now, like later. We are always open for like collaborations and thoughts. But think about this, like from this interesting complementarity and maybe duality perspective. Suppose we have a good system. We built a good system so that, like, as in view of the comments which I made before, everything is concentrated around the centroids of the classes. Suppose that these are my data points, but you know what? Even if I generate my data points, even if I take a different verification set or validation set, and even if I have a validation set, if I sample a validation set from my data, and my network is very good, it means that everything is going to be concentrated at a few data sort of clouds, data blobs here. You know, the consequence of that good and stable network is that, in some sense, it is extremely vulnerable now to the attacks I was presenting before, like in this particular picture, because all the data is going to be concentrated at just few points. And then it means that this M, which I was using in the theorem, here, this is the cardinality of my verification set. You know what? It doesn't have to be big here. So this M is going to be quite small, and this M is going to be proportional, in fact, to the number of classes which this good system is trained to classify. For example, if it's a binary classifier, it's going to be just 2. And that means that, in fact, even if I have an infinite data set, I will still have like verification set. And if my network is robust to adversarial examples in exactly the way as we discussed, that everything is concentrated around centroids, then it's likely to be extremely, perhaps, vulnerable to the other types of attacks where we, change the data structure. And that's the question which, which I think is very interesting to explore, because the question is that, is there an uncertainty principle here? Like, can you, in fact, defend against both types of attacks at the same time?
That is indeed a very good point. Thanks so much for that, that answer. Any other questions? Okay, and I don't think there's anything on the chat either. Great, so thanks a lot, Ivan, really appreciate it. This is a very fascinating topic indeed, and thank you again.
Thank you. Bye-bye.